Hey everybody, my name is Remy Staus. I'm a biomedical engineer and I serve as a team lead for the project 24007 and I also work on the filtration subsystem.
Hello, my name is Austin Russell. I am a biomedical engineering major and I am the electrical lead of this project. I work on most of the electrical components of the project and I also focus on the user interface subsystem.
Hello, my name is Melanie Pimentel. I am a mechanical engineering major. I am co-mechanical lead of the system and I did the Treadmill subsystem.
Hi, I'm Emma Faircloth. I'm a mechanical engineering major and I'm the co-mechanical lead for this project, and my subsystem was the sand redistribution treadmill.
Hi, my name is Alexis Henderson and I'm a biomedical engineering major. I'm the team procurement lead and I worked on the harness subsystem.
The goal for Team 24007 was to create a system to study how ambulating on different surfaces such as synthetic regolith and weights affects a rodent's gait. The material is synthetic regolith. That is the equivalent of sand found on Mars and Moon, and to mimic gravitational weights, we use a harness subsystem that shows Mars and Moon. The grand challenge of this project, however, was to ensure that there is a continuous system. The goal is to let the system run for 10 minutes. In order to do that, we needed to recycle the sand effectively from the bottom to the top and back down to the bottom. In our current solution, as seen in Dr. Margolis' laboratory, it's just a treadmill. There can't be sand on it, and it only runs just as a regular treadmill. So our solution in this project was able to solve that problem by using the sand redistribution treadmill in compliance with this treadmill system. Since this was such an integral part in our most minimum viable product, we came up with 3 separate designs. We ran a Q analysis, as seen right here, that showed the risks of each of those designs, and this one showed the least amount of risk, hence the reason for this project. At the end of the day, Team 24007 wanted to create effective solutions to meet the needs of our sponsors. Creating an effective solution did not only mean a functional system, but one that was also aesthetically pleasing, as we can see with the space background and stars, and one that is easily reproducible. Each subsystem, whether it be the harness, the treadmill, the sand redistribution treadmill, the filter, or the user interface, serve an integral component to this process. I will now let the team continue onwards with each of the subsystems.
Subsystem was designed to incorporate the FRT and harness subsystems while facilitating ambulation. Some challenges that we encountered were roller traction from the back, belt alignment slippage, as well as conveyor belt material.
The verification procedure of the treadmill ensures that it operates at the same speed as the rodent's ambulation. Additionally, it will operate at the same speed as the SRT. A strip of tape was placed on both the treadmill and SRT. A motor control then drove the system via knobs on the user interface to achieve a constant speed. A stopwatch was started once the tape reached the motor. After 5 complete cycles, the timer was stopped and calculations were performed to determine the speed. The percent error between the measured treadmill speed and the theoretical speed difference was then calculated, aiming for a value close to 0.
The SRT subsystem was designed to collect the regolith at one end of the treadmill and carry the regolith back up to the treadmill via a separate treadmill subsystem. The SRT needed to be angled underneath the treadmill to allow room for a filter subsystem, but not angled enough to allow the regolith to roll backwards down the sloped conveyor belt. The SRT uses compression between the SRT belt and the treadmill belt to transfer the regolith between the belts. Through the treadmill construction process, several improvements were made to the SRT subsystem. First, where the conveyor belt is inclined, the SRT had vibrations that caused the regolith to shift off the sides of the conveyor belt. To reduce the vibrations, a plastic sheet was added under the sloped part of the conveyor belt to stabilize the belt as it traveled up the slope. Rails were also added along the sides of the inclined conveyor belt to further reduce regolith loss. This was successful and did reduce the amount of regolith lost as it traveled up the inclined slope. Another improvement to the SRT was changing the conveyor belt material to material that is less stretchy and more textured. This helped keep the conveyor belt on the rollers, where before we had trouble with the conveyor belt walking off to the side of the roller. The texture on the conveyor belt helped reduce the regolith sand loss on the entire system. The top roller holders of the SRT subsystem were also adjusted so that the roller connected to the motor is straight and so that it is centered above the treadmill belt below. This helped keep the belts centered on each other and drastically reduce the walking of the conveyor belt. The verification procedures of the SRT treadmill subsystem focused on the collection and recycling of 95% of the regolith initially put on the treadmill. To do this, a set amount of regolith or sand testing material was measured and put on the treadmill system. The treadmill was ran for 10 minutes at a rat's running pace of approximately 19 centimeters per second. The material left on the belt after the runtime of 10 minutes was weighed and compared to the original measured weight. The SRT verification procedures also included the continuous transfer of regolith from the SRT subsystem to the treadmill subsystem and a component needed to be made that would smooth the top layer of regolith to a uniform height.
Verification procedures centered around the ability to remove 95% of the waste effectively. To satisfy this requirement, the team placed 20 raisins on the treadmill and observed how many raisins remained after 10 minutes. Verification results show that 100% of the raisins were effectively filtered through the system. The purpose of the filter subsystem is to successfully eliminate waste produced by the rodent. Solid waste, as represented by raisins, remains on the filter system, while sand easily passes through. It is a necessary subsystem as it helps enforce the cyclic nature of sand. The initial design was a mesh that is removable from the system. We also included a box sensor that can be used to collect material following the use of the system to aid in a more efficient cleanup.
We used the gravitational simulation model to determine what a necessary net force value we would need to observe on the force sensor was, as well as what the margin of error was for a 700-gram rat on Earth, Mars, and the Moon. Following that, we ran a gravitational simulation acceptance test and were able to simulate all gravitational forces within the margin of error determined by the analysis. The verification procedures for the harness subsystem focused on three main requirements: the ability to demonstrate that the harness and pulley system could hold 700 grams, accommodate gravitational simulations for Earth, Mars, and the Moon, and that these gravitational simulations match the force values calculated in the gravitational simulation model with an accuracy of 90%.
And so for our user interface, we chose a minimalistic approach. It's only 4 buttons and simple, pretty simple. It's run by an Arduino Uno with the program already installed onto it. And the Arduino Uno is just powered by a 5-volt supply. And all you need to do is, if you want to change the harness, you toggle to the harness mode, and you can raise or lower the harness depending on the force you need to apply. And we can switch to the treadmill, and this knob controls the treadmill speed for the stepper motor right here. And all you need to do is turn it on, and it'll start running. And there's a wide range of speeds that you can do, all the way up to the max speed of a rat. And the stepper motor that we're using right here is a NEMA 23, and it's a 3 Newton meter torque stepper motor, which we need to power the treadmills, especially when it's loaded with sand. And this is controlled by a 24 volt 3 amp power supply, and it's also connected to a DM332T digital stepper motor. And then up here we have a NEMA 23 as well, but only a 1.2 Newton meter, and all we're using this one for is to raise and lower the rat. And we chose this stepper motor because it has a high holding torque, which allows us to suspend the rat for an extended amount of time. And that's the user interface.
As seen through the teammates, Team 24007 constructed a treadmill designed to study how ambulating on different surfaces and weights affects a rodent's gait. To achieve this outcome, the team needed to stay proactive on tackling obstacles and hurdling the problems. By staying ahead and attacking these obstacles at once, the team was able to complete the project progressively. Because of the friendly user interface, the cyclic nature of the sand redistribution treadmill to the treadmill, and the clearly defined viewing areas for the plexiglass, the lab will be able to make advances in understanding rodent gait an inch closer to newly defined space travel, featuring rastronauts.